Colligative properties, freezing point depression, boiling point elevation. When we add a non-volatile solute, one that doesn't evaporate, so like sugar or salt or something like that, not something like acetone or alcohol, it causes the temperature range over which that substance is a liquid to become larger. So the freezing point goes down, the boiling point goes up. Lowered melting point, lower freezing point is called freezing point depression because it goes down. Boiling point elevation, the boiling point goes up. Now, what's interesting is that the amount that those temperatures change depends on how much solute there is, how many solute particles. It doesn't change with what the solute is. It's just the number of solute particles. These are called colligative properties. They're properties that depend on the number of dissolved particles, not on the type of particles. This kind of repeats the previous slide. Sorry about that. So adding salt to ice lowers the melting point. Did you observe that in lab when we made ice cream last week? Because the freezing point, the melting point of the ice and the water in the Ziploc bag was what? About 0, right? And when you added salt to it, what happened to the temperature? It went down. Seems kind of crazy, doesn't it? But that's what happens. So adding salt lowers the melting point. In Minnesota, where I grew up, they put salt on the roads in the winter to help melt the ice because it lowers the freezing point. That means that the ice will melt at a lower temperature.
But this definition is saying that it doesn't have to be salt.
It does not have to be salt.
It could be anything.
It could be sugar. It has to be something that dissolves in water. So some places they put sand on the roads. Sand doesn't melt the ice, it just gives you a little bit of traction. But it has to be something that's soluble. The advantage of ionic compounds is that they separate into ions, and it's the number of particles. So sodium chloride, 1 mole of sodium chloride gives you 2 moles of particles. 1 mole of calcium chloride gives us 3 moles of particles. And so that is going to be more effective than sodium chloride. It's the number of particles. Ethylene glycol is a common antifreeze. Why do you add antifreeze to the water in your radiator? To keep it from freezing and to keep it from boiling over, right? You've all seen cars at the side of the road. Maybe you've been unfortunate enough to be one. There's all this steam coming out of from under the hood of the car. The radiator's boiling over. There's a valve on the radiator cap that allows the pressure to escape instead of your radiator blowing up, which would be really bad. But if you don't have any coolant in, then the engine gets way too hot. So the ethylene glycol raises the boiling point of the water and it lowers the freezing point. So if it's really, really cold, the water in your radiator won't freeze. And when the engine gets really hot, and that happens a lot here in the summer, right? You got your air conditioning on, it's 115 outside. It raises the boiling point of the water so that your radiator won't boil over. So freezing point depression and boiling point elevation. For these properties, we measure concentrations not in moles per liter, but in moles per kilogram of solvent. And I'm just going to tell you about this so you can do the little calculation on your lab. I'm not going to give you a test question about this. This is called molality. It has the abbreviation lowercase m. I think this unit is just dumb on so many levels, but it exists, and so we have to talk about it. It's moles of solute per kilograms of solvent. It's very useful in some fields. In general chemistry, it's not useful except for colligative properties. So this is different in that it's a mass of solvent, not mass of solution. So if we calculate the molality of a sucrose solution containing 50.4 grams of sucrose and 332 kilograms of water. So let's go back and refresh our memory. Moles of solute to kilogram of solvent. So molality is lowercase m, which I think is not a good idea because that's also meter. Molality, moles of solute per kilogram of solvent. Here the solvent is water. The projector's buzzing at us. There's also some weird high-pitched humming thing going on. Well, that just, I don't know what it is. We'll just have to live with it. How do we figure out the moles of sucrose? They gave us a mass. 50.4 grams of sucrose. We're going to have to use the molar mass, which we calculated previously to be 342.3 grams per mole. So 50.4 divided by 342.3, 0.147 moles. So that's the moles of solute, 0.147 moles, and they gave us kilograms of solvent. So 0.147 divided by 0.332, 0.443 m. Molality, moles per kilogram. Any questions? We can calculate how much the freezing point changes or how much the boiling point changes using this equation. Here, delta TF is the change in the freezing point. This is always expressed as a positive number because we understand that the temperature goes down. M is the molality of the solution, and Kf is the freezing point depression constant, and that is going to be different for different solvents. This is the equation you need to calculate the molality of the salt solution in the ice cream lab. You measured the freezing point depression. That's the difference between the temperature of the ice without the salt and the temperature of the ice with the salt. Take the difference between those two numbers, make it a positive number. Kf, we look up. It's the value for water. And then we can solve for M. Here in this example, we're calculating the freezing point of an aqueous 2.6 molar sucrose solution. So a solution of sugar water is going to freeze at a lower temperature than water. That's why packing popsicles in ice is not going to keep them from melting, because the ice will fairly quickly come to 0 degrees Celsius. Popsicles melt at a temperature lower than that because they've got sugar and other solutes in them. So if we have a 2.6 molar sucrose solution, here's the freezing point depression constant for water. It's got funky units, but that's okay. They're going to work out with the units of the molality. So what we can calculate here, we've got that equation, change in freezing point equals molality times the freezing point depression constant. So here they gave us the molality, 2.6. Molal, that's moles per kilogram, times the constant, 1.86 degrees Celsius, kilograms per mole. So 2.6 times 1.86. So the change in the freezing point is 4.8 degrees. What's the question asking us for, though? The freezing point. Is this the freezing point? No, that's the change in the freezing point. What's the normal freezing point of water? 0. Adding a solute makes the freezing point go down, makes the boiling point go up. They spread apart so that the water stays liquid over a wider temperature range. So then the freezing point, I'll call it FP, the freezing point is minus 4.8 degrees Celsius. And the way I got that is I took the normal freezing point, which is 0, and I subtracted the change because I know that it goes down. Any questions? The boiling point goes up. Kind of already talked about those things. Same equation, different subscripts. The change in the boiling point is the molality times the boiling point elevation constant. Again, different solvents have different values of Kb. For water, that value is 0.512. You don't have to memorize that. We could calculate the boiling point of a 3.5 molar glucose solution. If you've ever made candy, you use a candy thermometer and you measure the temperature of the solution, it will get higher than the boiling point of water. It'll get above 100 degrees Celsius because the sugar raises the boiling point of the water. So a 3.5 molar solution, delta TB is the molality, 3.5 moles per kilogram, times the constant, 0.512 degrees Celsius, kilograms per mole. You see how those units cancel out? Leaving us with degrees Celsius. So the change in the boiling point is 3.5 times 0.512, 1.8. Is the boiling point of the solution 1.8 degrees? No. You have to take the boiling point of the pure solvent and add this. So it normally boils at 100 degrees, so then we're going to add the 1.8, and it's going to boil at 101.8. Any questions?